Hello. Today I'm talking with Jakob Zeitler, who graduated from his PhD this year and was part of the first cohort of students on the foundational AI CDT. Welcome, Jakob.
Yeah, thanks for having me.
So, at a high level, can you tell us what your research was about at UCL?
Happy to. Yeah. So what's my 1 2 minute pitch here? I applied to a PhD on the basis of being really interested about causal inference. And in causal inference, we're very straight up interested in causes and effects, and we want to quantify that. So we want to find mathematical ways to characterize those relationships, and then figure out, whether A causes B or B causes A, and then also how much does A cause B. And of course, the world isn't just an A and a B, but there was a C, D, E, F, G, and a lot of different variables. So in medicine, for example, you'd be interested in, does this drug work? When I run a clinical trial, how effective is that aspirin on reducing headache? But then also in a marketing campaign, I want to know whether this color or that color or a certain kind of discount code reduces, better results, let's say for an e-commerce platform. And so I was really interested in working on that. And halfway through, then also expanded into methods of experimentation specifically. That was something called Bayesian optimization. And so essentially emerged from my PhD with two very nice strong pillars in causal inference and active learning.
Nice. So, in the causal inference stuff, what were your A's, B's, and C's that you were looking at?
Well, we looked at it from a very fundamental lens. So, if you're an epidemiologist looking at the disease spread, you might be looking at how, certain people coming together in big spaces, causes certain, disease spread. There's public health. There's all kinds of applications for causal inference in medicine and industry, optimizing server farms or figure out the fault why a semiconductor production machine failed. But because I was on the theoretical level, we drilled really deep into what the limits are of causal inference. So how much can we say about a causal relationship given certain data and assumption? And that was, hugely fascinating, hugely intellectually stimulating. And I learned a lot about the limits of not just causal inference, but also statistics and machine learning. So there's no specific A and B. We looked at every A and B, and in fact, most of the time it was just as abstract as A and B, without
Hmm.
any specific meaning, but the applications were just as important.
I see. So what an example in the epidemiology would be wearing masks. So there was a lot of debate about whether masks reduce disease spread. And in the ideal case, you would do a randomized controlled trial, but that's not really feasible or ethical in the middle of a pandemic to force some people to wear masks and force others to not wear masks. So the idea is that just given observational data that you've collected, can you draw some insight into whether masks caused a reduction in disease or not? So my understanding is that you're looking at like under what conditions can I draw these inferences in general, not just in the case of masks?
Yeah, that is actually, yeah, it's very accurate. Absolutely. So the max example is a good example. That's an example where causal inference is, specifically of interest because we can't experiment, as you say. And indeed, these conditions or assumptions that we have to make to come to some kind of results are really of interest of study in causal inference.
Mm-hmm. So what was your, can you share with us a key insight about the kind of assumptions you can or have to make?
Yeah, absolutely. This is, in fact, what I'm most passionate about and what I spent my PhD thesis writing on. And essentially, there's a first categorization, which is we have assumptions that we can empirically validate. So we can go out in the world, measure data about, let's say, people wearing masks or not. But then there are also assumptions that we can empirically very hard validate or not at all. And those are the really interesting ones because we need to make crisp results. We put in data and these assumptions into a model, and then the model says, wearing masks does reduce the spread of COVID. But then we can't really validate them. So what does that mean? Well, that's where we have to move on to then when work with subject matter experts. So in terms of the maths, there might be, physicists about, particle spread or something like that, that can give insight into whether these assumptions are reasonable or not, given, our current state of the knowledge of the world. And so this is incredibly crucial, and anyone serious in causal inference will always emphasize that it is absolutely necessary to talk with the subject matter experts to make sure that these assumptions that we can validate by collecting data are the best in terms of what they are justified. The end game there ultimately, though, is more something called sensitivity analysis. And that is where we look at models with different assumptions. We have a model A, model B, model C, and these three models, we will give them different assumptions. Some of them will have more, some of them will have less. So the results they will give will also differ. And then we can choose between those models the one that we think is most justified. And sometimes that means we choose a model that actually is not giving us great results, is saying, I don't really know. But at least we're scientifically sound. We're scientifically saying that we don't have enough data and or validated assumptions to make a statement here. And that's what I think is good science.
I see. So the idea would be that you would come to an epidemiologist and say, if you can assume X, Y, and Z, then you can say this. If you only assume X and Y, you can say only this. And if you only assume X, then you have this much weaker result. And then you have a back and forth with the epidemiologist about which of these X, Y, and Z are actually reasonable assumptions.
That's 100% correct. Couldn't have said it myself any better.
Okay, nice. So that was the causal inference side, and then you had Bayesian inference as well. But I understand that was also connected. Could you tell us a bit about what you were doing there?
Yeah, absolutely. So, motivated by the observation that we need to make these very strong assumptions in causal inference to come to results that seem actionable. I wanted to expand into more assumption weak environments for statistics, and specifically that would be areas where we have control over the whole system, such as a laboratory, where we can set the temperature and we can set the ingredients and so forth. And so that way we can kind of sidestep the causal inference assumptions we'd have to make if we didn't have control over the system, and we can focus more on actually getting the most out of whatever system we're studying. Let's say a chemical reaction, a solid state chemistry, some alloy system. And so because we now basically implicitly have all these causal inference assumptions already validated, because we're controlling all inputs, we can now focus on the most data efficient way to explore a high dimensional space. So you could literally just think about it as baking. I want to make some brownies. I need the right amount of sugar, right amount of cocoa powder and flour and water, and then the right temperature, and then also the right time in the oven. So how do we make the perfect brownie? Well, that's a question in itself with a mathematical answer to it. And in fact, it is a common running joke in data science and statistics to have papers that showcase new methods by answering the question of, how do you make the best brownie? Or another popular one is, what's the best mojito cocktail? Of course, scientists love to actually go hands-on and, make those experiments themselves. But long story short, those methods are extremely exciting because they will help us solve a whole bunch of really important problems. Let's say in materials, well, we're still due to find ever better catalysts, or in medicine for drug discovery, and not just finding new drugs, but also how to scale up their production. And scale up is particularly interesting to me right now, since it's such a hard question. So we take, a chemical process from 1 microliter to 1,000 liters. Well, how do the chemical properties change, and so forth? And that's really a data-driven question. And these are the things that I'm concerned about.
I see. So if I think about the brownie case, if I was an experienced chef and I cooked some brownies and I thought they were not good, I would have a theory for what ingredients I should increase or decrease. Maybe I think they're not holding together well enough, so they need more gluten or egg or whatever. But do I understand it correctly that Bayesian inference works in cases where you don't have a theory like that, and it just somehow intelligently guesses what would be a good recipe to try next based on simply the quality of the brownie, not any indicator of what ingredient should be increased or decreased?
Yeah, I think that's a very good question, and in fact, it's getting at the core of Bayesian optimization, and its adoption problem, right? So at the end of the day, unless you're very rich in budget as a pharma company, but even then, you will have to deal with human experts, and that's not necessarily a bad thing. So a human expert will have intuition over 10, 20 years. A lot of pharma companies have extremely well-trained people that have a really good feel for chemical processes. So what is kind of like at opposites there is that on the other side, we have evidence where even experts are shown, to underperform because they might have developed a bias about a certain chemical reaction 10 years ago, and they just simply don't know that there's a slight modification that, would actually improve the performance. And so Bayesian optimization doesn't have any bias. It just goes and maximally explores a high dimensional space. So it has absolutely no opinion about chemistry. It's really dumb in a sense, in that sense. But what it does, it has, a prediction about what it thinks certain, brownie, baking recipes perform like. They're not, perfect, but those, some of those predictions are more accurate than others. And then it also has an uncertainty about that. So it might be like, this is a really good recipe, and I'm also certain about it. It might be like, this is a good alternative recipe, but I'm less certain about it. And so Bayesian optimization then will say, okay, let me go over there and try this new brownie recipe, which I think might be good, but I'm not too certain. But I want to, increase the certainty about this space. And so when it comes to experts, there's basically many different ways to go about it. We'll see that some experts really embrace the model. That's really interesting. It's in some way, it's similar to this kind of like move 34 thing in AlphaGo. I don't know if you
Mm.
remember this story, but
Yeah.
where AlphaGo kind of like did this move very early on where people said this is a rookie mistake, and then it turned out to win the game. Whether AlphaGo actually understands Go or not, it's not of concern here, but we had the same thing where the Bayesian optimization recommended two experiments where two chemists said this doesn't make sense. This is not theoretically, valid. Yet they still embraced it, ran the experiment, and lo and behold, it actually found a space in the chemical space where, despite increasing this acid to a level where this reaction shouldn't work, they still got the same performance, which was, definitely, at odds with what their knowledge was. But again, as a good scientist, you just embrace that and be like, that's fascinating. I want to learn more, why that was wrong.
So in this example, you had chemists that were trying to make a reaction go as quickly as possible.
Yeah, to make a certain kind of material, perform in the best maximal way. Yeah.
Ah, okay. What material was it?
It's a world leader in afterglow material. So it's something that traps photons and then emits it. You might know from the stars in your children's bedroom,
Yeah.
that, they take the light and then they emit it at a later stage. And you want that to either be as long as possible, or you want it to be as bright as possible. And those are actually, it's a multi-objective problem. So the longer it glows, the less bright it will be afterwards. And you will kind of push this Pareto front. I know it's a complicated concept sometimes, but two performance indicators, and you want to push that further up.
Hmm.
So when you turn off the light, it should glow really strong, but it should also still glow after 8 hours. Um,
Hmm.
and that was the project that was super exciting to work on. And indeed, I think they also did manage to learn a lot through Bayesian optimization there. Yeah.
Yeah, that's super fascinating. Did some of that work make it into your thesis?
It did not. No, this was a separate industry work I was doing, and that was, yeah, that was, yeah. I mean, none of that is public. That's industry work.
Okay, so you've told me as much as I'm allowed to know.
In a sense, yes.
And so was this Matterhorn, or is Matterhorn something else?
Correct. Yeah. So this was in fact the first project I worked on. This is the reason why Matterhorn was started in the first place. Matterhorn wasn't started first, and then this project came around. This project came around through a friend, and it fit just really, really well in many respects. And to work with another friend on this project, I had to register a company, and that's what I did. So through the company, I could then, do the usual business stuff, write invoices, and handle it on a accounting side.
Yeah, that's really cool when your research has such a promising result or good result that you spin it up into a company. So how come you chose the
Yeah.
name Matterhorn for your company?
Yeah, so that's because the first customer is from Switzerland. And it also felt like, at that point we were very much focused on materials, materials horn, which is like matter horn, which is peak materials. So
Ah,
we
okay.
were hoping to find peak material performance. And in fact, of course, in Bayesian optimization, you're also trying to find, the peaks and the functions that you're learning. So that's the idea.
Mm,
And it
hmm.
turns out it's incredibly powerful marketing because everyone assumes you're from Switzerland, even if you tell them you're not. They just love the story. So
They assume you've got that Swiss funding.
yeah, exactly. Yeah, and yeah, it's great. Yeah.
So you also did an internship at Spotify, also doing causal inference. Can you tell us a little bit about what you did there?
Yeah, that's right. It feels like I almost forgot, but yeah, in 2022, I had the chance to work with Kieran at Spotify Research, and Spotify is uh, I think they're a great company that are very like impact focused. So they're not gonna, adopt any kind of like research fad just for the sake of doing their research. So they saw value
Hmm.
in causal inference. And I had a chance to be there for 3 months and work with Kieran as one of the very few people in that causal inference lab. And it was great because it was the first time I kind of like went, into the cold deep water, into a new topic in causal inference, and trying to, make a contribution in 3 months' time. And I didn't think it was possible, but in fact, it was probably the most productive time of my PhD, which is
Wow.
still a lesson that I literally wrote down because at that point in time, I had been working on interesting things, but that didn't come to a paper or a publication. Yet at Spotify, we worked on something for less than 3 months, submitted a paper, got it published, and it wasn't just a random paper, but it was something which I think had a very reasonable, important contribution. And then on top of that, also had 2 patent registrations. So all of that in less 3 months just felt absolutely crazy. And that was simply possible, first of all, down to luck, but then also down to picking the right research strategy. So choose your topics, rank them most important, most relevant, and then just start from the top. And that's what we did for something called synthetic control. And yeah, that was great. So I can share more about that. Long story short, I do think that when you find that topic that's relevant and interesting, it's going to have a great impact and you're also going to enjoy working on it. So it's these two kind of measures you want to really optimize for. And the third one is probably working with the most interesting and best people on it. So there's a important and hard to observe fact that if you enjoy working with the people that you have to do these things with, it's going to be 10 times more fun. You're going to be 10 times more productive. So this kind of like the trifecta is like the right people in the room with the right relevant problem and something that's interesting to everyone involved. And then you just press play and it plays by itself.
Yeah, that's a magic recipe. If you can
Yeah,
get that, you're golden.
absolutely.
So what was the content of the patents?
Yeah. So the first one was in fact just based on the paper, so that's all public. The American patent system is rather public in its approach.
Hmm.
I think America is one of the few countries where invention disclosure matters first. So it's not that you run to the patent office first, but it's that you put it out in the public first. Something like that. I don't actually remember details. Don't quote me on that. But the paper was out there, and then the patent followed, which was on method in synthetic control, specifically around sensitivity analysis. I mentioned sensitivity analysis before already. So you look at the model and you change the assumptions and you want to see, okay, what's the impact? Does that change my results? And so that was just packaged up in a patent. It's a paper written up as a patent. The paper is less than 10 pages. I think the patent is 100 pages. Patent law
Oh,
operates a
wow.
little bit different. um, But the other pattern is an even more crazy story, which is essentially that Spotify runs these quarterly hackathons, and so you get a day or two to just drop your work and work on something you always wanted to do.
Hmm.
And so before that, there's a run up where people put together teams. I think there was like 15 teams, and one of them was called language learning via music. And that is something that I always wanted to do. I had so many ideas about it. Like I experienced myself through language learning that once you get on the level where you like listen to a song in a different language, you kind of like it's just really fun. If you like the song, you look up the lyrics and you look at the words that you don't know, and like those words you just never forget. Like it's
Hmm.
like instant vocabulary learning. You remember the song, you remember the words, and then you remember the vocabulary. And so that's kind of what I wanted to exploit. And I found actually 9 other people in Spotify that wanted to work on the same thing. And so it started out on a Monday with a quick one call. People were pitching their ideas, and it was like, guys, how about we put the lyrics on there scrolling? And so that's already possible, right? On any kind of like music streaming service, you just see the lyrics. But when you tap on it, you can actually see the translation of the word. And then on top of that, um, some of the words will be translated gradually. So like the lyrics will be kind of jumbled up where like some things will be in English, but others will be in Spanish. So like we learn kind of a degree of how many words you already know. And so that way when someone's scrolling, they might see like the lyrics in English, but then they see a Spanish word and they're like, oh, that's I can guess that word from context. And so that's like
Yeah.
the most powerful language learning. And so 2 days with 10 people, man, like they get to work. So I actually dropped off to do something else. And like the next day, the whole prototype was ready. It was slide sets and presentation. That was just this one conversation on a Monday morning that led to like a whole prototype for this. Is this going to be released? I hope so someday, but the, very strict priorities about feature sets and Spotify and language learning is not something I think that's on the top there right now. But if you ever see something related to language learning in Spotify or any other music streaming service, then it's most likely based on that 1 hour in 2022 where I sat down in a room with a bunch of people.
Nice.
Yeah.
So that was part of a patent as well?
hmm Went into a patent, registered, everything like that. Yeah.
Okay, nice. And then, okay, so these two patents came out of it. There was a paper that came out of it. Uh, yeah,
Mm.
this just sounds like an incredible 3-month internship.
Yeah, absolutely. Yeah, it's absolute outlier.
Nice, nice. Um, so another success you had was you won first prize in the G Research thesis competition.
Yes.
Did that come as a surprise to you?
Yes and no. I was actually very strategic about that, but essentially that G Research is putting out a lot of competitions and they're really trying to make a big impact in the PhD market. Let's say that, it's a talent market and you need to show presence. G Research isn't the only one. The Citadel, Jane Street, everyone's got their free t-shirts. But of course, some of them have more impact. And G Research, I think, are quite focused on the UK, in Europe. And they put out a competition for UCL, and it was going to be a 5-minute video, and it was very clear that like the more time you put into it, the better your chances are. So quickly did a brainstorm, and actually together with my wife came up with a really cool idea how to structure presenting my research in less than 5 minutes. I did
Hmm.
that actually on holiday in a hotel room. That was quite funny. You can see it in the video, but it's a hotel room. Um, and just the focus was actually on trying to make it as simple as possible. So this was more of a science communication exercise than like a hard functional analysis, matrix algebra, whatever.
Yeah, I like the answer that you might have expected to win, but
Yes, yeah,
but it makes sense if there's strategy involved. Um,
yeah.
can you tell us about Biomed?
Biomed, smart biomed.
Yes.
Yes. Okay. So graduated from UCL. And I got this really amazing offer to continue at Oxford at a new emerging project called Smart Biomed. Denmark is heavily investing in science right now, and they're setting up these pioneer centers. There's 4 now, and Smart Biomed is the 4th and the last to be founded. They have one for AI, I think one for materials, and Smart Biomed focuses on I forgot what the exact acronym is, statistical methods for healthcare and problems in complex disease or something like that. And so that role here is based in Oxford. It's connected to a center that's also in Aarhus and Copenhagen. So it's a triangle between Denmark and the UK. And so at the statistics department here, I get to continue the research in course entrance and Bayesian optimization. A lot of freedom and a lot of, again, great people to work with, engage with on a regular basis. And yeah, it's a great position to continue the work.
So this is part of your postdoc that you're now doing at Oxford?
Correct. Yeah, it's a postdoc role. Yeah. What came together there was really that that what topic you choose in your PhD does have an influence, and you don't necessarily want to choose a topic that's kind of like on the way out. So like if you chose, let's say if you go into a PhD in 2022 and you're choosing to do NLP, and there's already science that large language models are completely going to swamp the field. That's probably not a smart choice. What instead you want to do is you want to choose something that's like up and coming and promising, but not necessarily has reached its peak yet. And so course inference was exactly that in 2017, 18, 19. So I started my journey in course inference before UCL and continued there. And in 2019, course inference wasn't interesting to most people. It was this very obscure thing. But then, of course, at the end of the PhD, as it travels and grows in interest, I mean, one example was that the course inference workshop at NURBS in 2022 was 1 room, and then in 2023 it was 3 rooms. So it was both in New Orleans, and it tripled in size, and that just showed how much impact that had made. And then, of course, when you then emerge and submit your thesis in course inference, it opens a lot of doors suddenly because it's a topic that's fundable, a topic that people are interested in to make a difference to. So I mean, that's the one thing of being strategic about. The other thing is, of course, it's a lot of down to luck. I already lived in Oxford. I already was in the UK. I was graduating just around that time. So time and place is something that's hard to control to get the best position, but it worked out this time, and so I'm just really grateful for that.
Nice, yeah. Congratulations on getting the position.